All right, we are live again for Nand2Tetris, week 5. So where were we? Last week we ended off basically with a test of this Max.asm. So we tried a different assembly program and compiling that down to binary, and we compared this against the results, and that passes. So I'd like to take these and make those proper tests. I think we found one issue, and that was with this label here. That kind of broke our convention of all capitals means it's a label. It has a number, and we could have still kind of tried to make it work, like capitals plus numbers or whatnot. But then I kind of realized once we get to the compiler phase, these labels aren't going to be as well behaved. So we might end up having um, like class names and method names and whatnot, and that's not going to be all uppercase. So we've just got to drop that convention. So that means any any semantics we put on a symbol that's been parsed comes purely from context, right? Uh, we can't decide until we've made a first pass through whether or not a thing is a label. So we make one pass to find the labels now, and then another pass to then find the variables. Uh, Let me skip my music a bit. Okay, so what are we doing today? I think we're going to go ahead and try to make a proper test files. I did also just download. Should be in there somewhere. Yeah, so I downloaded several assembly files. The biggest one of this, which is Pong. Okay, look at that, look at that. Ooh, this has like memory deallocation calls. We'll implement that at a higher level. Um, but yeah, I'd like to compile all of these to binaries. And I don't have a binary for this to test against. I do have binaries for all of the other versions. Let me see. Hmm, 1 second. Do I have? Okay, dot hack is my binaries. So I have something I could write tests against. Um, Jeez, give me a second. This music is super distracting. Let me try a different. Hold on, here we go. And then after that, I think I'd like to get into actually running these binaries and getting our state machine working. So let's look at our this into like doing some transitions here. I might take a detour before that to fix my integer types. I have several that are just basically aliases on int, and I'd like to turn those into an opaque type of some sort. So we'll think through that. I'll take inspiration from what I did with Cinecore, and perhaps I'll pull up that code. So for now, let's make a test. So we'll do it based on whatever's going on in this worksheet here. So in here, I probably just want to clean up some of the code to separate things into multiple files. So today is a bit of cleaning and testing stuff I'd wanted to do last week, and then design work on the emulator state machine itself. Hmm. Okay. Um, so here we have an assembly, and we parse that as a program, an assembly program. And then we use that to create our simple table. We dereference that and make a new version of the program. Oh yeah, I had the thought that dereferencing could also mean we just turn it into a list of like the basic instructions. Yes, let's also take out the comments and the labels. So instead of a program, well, I guess a dereference program is then just a list of pure instructions, and every A instruction in that case should be, oh, excuse me. Okay, and then every A instruction in that case should actually be a constant at that point. So we could do a check when we dereference every time a program is dereferenced. There are no more A instructions. Um, this might be a case where I play around with some property-based tests. I can test it properly like that. Although ideally, I would just like that to be in the type system. But that's a problem for that. Don't go down too many rabbit holes, or at least I want to go down into those rabbit holes intentionally, and I don't think that's the intention for this episode. Okay, so after that, we turn it into an ML program, which is a list of M instructions, which we can then print as binary or whatever. And in this case here, I had this kind of useful thing. It shows a binary. It shows the instruction that was parsed, and then this representation. So this one means like set D to this and Y, right? The whatever the two inputs to the ALU were, which I like, and I think I'll integrate that into a nicer interface later, nicer like debugging interface. Uh, this is the kind of stuff that maybe we'll make it into once we're doing a visual emulator into like a web app. I might put that in there. And I think it actually, you know what? I'd like to print actual assembly that's being translated here. It's not exactly straightforward to do that because we have to keep track of what line things came from, and we don't currently do that. So, I mean, we could break it down by line, where each line, when I say line, I mean like memory step. Each memory step has like an instruction, maybe some labels, maybe some comments. Then it would be one-to-one with the output. Because each one of those, I hesitate to do that necessarily though, because at some point we might introduce meta instructions, or like not meta instructions. What's the word? Like macro assembly instructions. So that will take a little bit of design work, and I'll think about that. Eventually, we should add that. Let's add that to our README wish list. What is that like? Assembly macros, and then line chunking. Some line chunk. Comment / label inst. Yeah. Okay. That is mentioned. And one of these days off stream, I'll clean up that README and give ourselves like more of a roadmap. But for today, I think we have enough of a roadmap to work with. So let's go to the tests. Test. We'll work with this my suite. All right, let's just test a very simple Max.asm compiles. Exactly. All right, and let's take a look at that Max.asm. I'll just pull them both up. So there's the assembly, and then max.hack, and that is what that turns into. And this is what I mean by the line chunking. Like these two correspond to line 1, and like these two would correspond to line, I don't know. But if I want to show the original instructions and not just the dereference A, I could show the dereference instructions alongside of this. But for that, I'd have to have a way. I think either way, I should make a way to print assembly instructions in a nice way. So let's look at this here. This here is an assembly instruction, and we're basically just seeing the case class. And yeah, we basically just do like an inverse of parsing. I think parsing and then printing should return the original result. Should be 1-to-1. I don't know if we lose any information there. Like maybe it's possible to lose specifics. I don't think so. Alrighty. So let's pull out the file. I have source from resource. And Max.asm lines to list. There we go. Let's do the same with hack lines. There we go. And now it knows what we want. Cool, cool, cool. We get our table, we dereference, and now when we dereference, it's just a list of instructions. So maybe I'll do a little print there, and the ML program. And we take the ML program, which what is this? This is a list of instructions. We turn that to binary map to binary. And let's make string, and that should match. And then, oh, you know what? No, we can just do this. So binary lines. I guess we could do a for each on everything. Sure. All right, let's test that. What's going on here? From resource is not a member of. Source.from resource. Oh, we have a capitalization here. Oh, this program.parse. Ah, right. It's just a whole thing. Okay, let's just get this as a whole file. So get lines.make string, or we can just do. Can we just toString this? Well, that does that does compile. So let's give it a shot. And I suppose we could extract that into a generic test. All right, we have a failed test. Illegal argument exception. Rich has no case with name iterator. Oh, okay. This just becomes an iterator. So this from resource gets us what? A source, which I guess is basically an iterator. We'll just get lines and then make string for the new line. Sure. Let's rename this. Let's call this raw.asm. Call this raw hack. Alrighty. And here, I suppose we could say binary map to binary dot make string. And now we can just test insert. We shouldn't have to do raw hack that makes string. We've already done that. Actually, I do like this being a list because I want more granularity when things fail. So to binary zip or yeah, sure. So we're gonna rip that together. And we run the test against each line. Cool. Enum, Reg has no case with name. What's going on here? Let's print the ASM. Or you know what? We can actually just run this whole thing in a worksheet. Let's run this in a new worksheet. So let's save this old worksheet as just, I know. And this is the one in which we actually run our tests. Okay, so what does raw.asm look like? Okay, and what did it struggle with parsing? Just an empty string. All right, let's look at our parse function. Let's filter out empty strings. Dot filter, not empty. I guess we could also strip white space there. Should we strip white space on everything? Probably. Yeah, in fact, we're already doing that here when we parse. I suppose it could be an option of a line. Right, if it's not a comment or label, it assumes it's an instruction, and if it's an empty line, then that's no good. So we're going to filter so that dot strip dot not empty. I would do it. There's a repeated strip. I don't really care. Oops. Okay, much better. I think that should fix our test too when we run it. Ooh, not quite. There is a little diff. Obtained. All right. I need this test to be a little bit easier to debug. So let's get line numbers. Um, hmm. How do you want to do this? I suppose we could just print the line number as we're doing it. If each of those are zipped with index, I would also do it. I'll do it in a pinch. We'll clean it up later. All right. So the tuple. Okay, it tells us there's a difference in the tuple at index 0, the very first number. All right, so this one starts off with 0, 0, 0, 0. What does that mean? So this is at R0. Right. Let's take a look at the individual steps as we're doing this. So we'll go here. Let's give myself more space. Oops. Um, where do we actually want to do that? Here's the ML program. The very first instruction is D sets to 0. That's not quite right, because the very first instruction should be an A instruction. So we have lost our A instructions. Let's see. Program. Let's see this program for each print line. Okay, comments, comments, comments. And then the first thing we have is D equals RO minus R1. And then we have the A instruction. And then the A instruction R0. And then the C instruction and the A instruction R1. That's strange. We're getting them in the wrong order. Okay, let's look at the dereference program. Oh, wait, here we're back to normal. A instruction 0, C instruction. Okay, let's filter out the comments of this. So program.collect case inst. And we'll just print that inst itself. Or I guess, this could just be a for each. Okay, it does start with main instruction. I didn't know what I was seeing. Oh, right. That D that we were seeing, that D equals RO minus R1 was a comment. So filtering out that's why filtering out the comments helps here. I should just use a pound symbol for my comments. So that does look correct. It looks like the right instructions. And the deref program looks correct as well. I suppose we could zip all of these together. So like this is just the instructions. Let's do like val raw instructions. Then we'll just take program.collect. Yeah. And this is just raw instructions for each print line. Now we can like zip it together and see the progression. In fact, let's do that. So binary lines.zip. With the ML program. One sec here. The dereference program. Okay. Now here. binary lines, binary ML, deref, and raw. Cool. Let's see what this looks like. Oh, right. So this is dereferenced. We still don't have a nice way to print the actual assembly itself, but that's the right idea. And at least see where something might be going wrong. Um, and according to this, the first thing that's going wrong is the very first instruction. And it looks like after that, it is fine. Maybe not. No, no. An A instruction actually should not be starting off with 111. Yeah, that's translating into the wrong machine instruction altogether. Which strikes me as odd because I thought that's I know what we got working last time. Um, right, we tested this. Like this boolean equals true. This is the expected output. And the generate binary. So we do 2ml and then turn it to binary. We parse the ASM, program parse ASM, map to binary. That's exactly what we're doing here. So what happens differently then from this in our test? Okay, looking at the test down here in the bottom left. Um, no, actually, we don't want to look at that. I think I want to look at what we were playing around with last week. So we turn 2ml right to binary. You reference program the same way. Program that parse the assembly. Oh, hold up, hold up. Do we even use this deref program? I don't think we need to use this deref program. ASM.2ml is supposed to take a normal program. What did we do here? Program.parse ASM. We never use program.parse. And then that's what we should turn to ML. Right, I guess 2ml already works on a full program. And here we were instead doing it on the dereference program. Strange. Okay, so raw. Um, raw ASM. No, no, no. We've already parsed, I guess just the program, or rather the ASM program. Okay, now this looks correct. All right, well, that's something I would have liked to catch with type errors. Let's rename this program. This is a ASM program. And I guess we don't need these two because we just 2ml the ASM program. All right, so now the test should pass. Cool, test passes. Um, That does look like a nice thing to have for, I don't know, some other sort of debug. We could write tests for just the dereferencing or the table itself. But yeah, I had to make a note of, I'm making a mental note of that possibility here. ASM program, ML program, and then here are the binary lines. Cool. So I guess you want to make that a separate test. So def so ASM file name and hack file. Cool. All right, now this test here can just test assembly with those names. Um, cool. Now we can just have tests for all of them. Turn off display worksheet. What else is there? Test. Oh, we could test Max.asm. But so Max.l is the dereferenced one. So like what we could test is take our assembly, dereference it, print it back out as assembly, and test that matches blank L, like the L version. I don't know if I have a Pong L. Do I have a Pong L? You do have a Pong L. So that'll be useful as a test there. We can make that a generic test, but for now, what we actually want is add and rect. Cool. And test rect. Okay, so those work. We had a failure. We had several failures. All right, let's just do this in full REPL. All right, so which test failed? Add.asm fails. So where do we have a line that's different? Oh, this zip with index is not being helpful. Let's just get rid of that. How do I get the line in the error message here? Can assert equals take an extra? There's a clue. Okay, yeah. Let's do that. Let's zip the whole thing. So zip those two together, add the index. So we have the binary, we have the hack, and then we have index. And there we go, line. Yeah, line starting at 0. Let's see what the test says now. And I will pull up add.asm and add.hack. They are very small. Okay, at line 0, very first line, binary You know, raw's not quite the right name. This is our it's not raw. Um, Whatever. We'll think of something. But our binary is compiled binary and raw is like the original, the standard. I guess we call it expected. And then we'll just rename this to expected. That's better. And let's call this generated binary. Cool. That's better. Better semantics there. Okay, so right at line 0. That makes sense. That should be what we get. Let's print the whole thing in the test so we're seeing what's going on here. So let's take the ASM program dot filter. I don't know. Collect case. And then we'll zip the ML program. Yep, that's exactly what I want to do. And then let's do a print line for each ASM and ML. Cool. It knows what I want. So we can look at the whole program. Wait, what? That is so much longer. Add.asm should be short. Oh wait, no, this is for a different program. So that was for whatever ran. This looks like it was the I don't know which one that was. Was it the rectangle? Anyway, I'll just comment out these for a sec. We'll focus on add. Okay, so we fail right at line 0. Here's the program we're generating. It's much shorter. We are losing those are all C instructions. We are losing the A instructions altogether. Let's look at the ASM program that we're parsing. So ASM program for each print line. Ants 3. Add ants 0. Cool. So how about once we parse that? Well, no, that is parsed. So once we turn it into ML, we lose things. Yeah, we did lose the A instructions when we turned it to ML. Okay, I guess we need to have more granular tests to catch these things. So I'm going to take a quick bathroom break, and I'll leave that up to think about. All right, we're back. And it's occurred to me that this is the first time we use an A instruction that is a constant, right? We didn't dereference that first, and this makes the earlier bug make more sense when we just dereferenced first, and then we tried to turn the dereference program into ML. Um, that didn't work because all the A instructions in the dereference are doing this exactly with just the constants. So we found a bug. We found a bug. Um, so A instruction with a constant. Well, I mean, it exists. It's here. So here we dereference the program first. Okay, it must be when we dereference the program. So when we dereference a program and we dereference symbols, cool. Uh, that does work. Otherwise, any other instruction, we assume it's a C instruction. It's literally just any other instruction at all. So we can just say um, inst. That's our bug right there. Okay, let's see what happens. Cool, cool. Mm-hmm. I think eventually I would like to make the reference program a type in itself. I prevent that bug from earlier. But now actually if we were to pass in the dereference program to this, like if you dereference the dereference program, then you should get the same thing back. So I'll have that as a test. We can remove these print lines. I'm gonna leave this commented because I kind of like it, and maybe we'll run into bugs again. It's very helpful for debug. Okay, let's see all those pass. You know what? I think I'll leave this in the output. It's kind of cool to see it. Yeah. In fact, let's give it a name. And then maybe this will be like, I don't know. Eventually, this should just be logged in assembler. We'll leave that as a to-do. Assembling ASM file. Right. Nope. Okay. Cool. Assembling Add.asm, assembling Rect.asm. We could test just the dereferencing. I also want to test that dereferencing something to itself. The referencing should be idempotent. Deref program, deref again. and deref should equal deref again. And then I guess we could test the dereferencer. So test deref. So we've got two. We're defining a function here. So we've got like a ASM file, and we have an ASML file. Okay, so I think we'll just parse both of them. So val ASM, we didn't want all of that. ASML, and then we do those ASML program. And then we parse the ASML. Okay, and then we compare those against each other. And then we test each of those. Um, cool, and we'll do that for each of those. So Max.asm, Scala.asm, add, and we'll do the same thing for Rect. Okay, cool. We ran into an issue. That was just with this, right? Not any other tests. Let's just try it with add. Smallest one. Oh, there's no add L, is there? Let's start L.asm. You have Max, Pong, and Rect. Okay, let's try with Max. Oh, and then we can do this with Pong. So let's start with Max. Okay, this fails. Where's our failure message? Line 0, against 0 is not equal to something. Alrighty. Expected was just empty. So this is going to be a list of instructions. Let's just do a quick assert here. Assert expected deref program, not for all. Yeah. Did you mean expect? Yeah, for all. I do want to see what's coming out of those. So let's just we'll do a quick print line on each. So maybe let's start with the ASM programs. ASM program. And then we'll do the ref program for each print line. And I expect it. And let's give them some names. ASM. Referenced. And expected dereferenced. Sure. I'll just print the whole thing out. So we run the test deref. Where is it? Oh, we failed that assertion here right away. Contain only instructions. Oh, okay. I guess it has some empty lines in there. Yeah, it has some empty lines. So I guess when we parse a program, what's this expected? When you parse a program, no, 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 no. Hmm. Let's remove this assertion. It fails, but I want to see what it's actually failing on. Okay, it does have a bunch of comments. So I suppose it also does need to be dereferenced. Here's the expected dereferenced, I see. Yeah. Okay, so we filter out, we do still need to filter out of this. So dot filter, or I guess we do a collect case instruction. Yeah, we just collect all the instructions. Not assertions of pass. Cool. Yeah, I don't think we need this. Now we can test that for, not add, we can test it for rect. And we can test it for Pong, the big program. Pong with Pong L. Cool. Um, I like that. All right. I think this is a pretty happy test suite. What other kind of things we could, I mean, we could do more tests in the symbol table itself. I don't know. I'm happy that dereferencing is idempotent. I'd still like to have a dereference program type itself. right? Again, we ran into an issue here. Like that dereference program we were testing against had the comments in it still. So when we construct a dereference program, I'd like to follow those constraints. We can't just kind of like loosely hand wave and say like, oh, this list of things is a dereference program, you know? Um, where's deref? We'll add that as a comment. Uh, .deref to do deref program should be its own type. All right, that can be in our wish list, our list of issues. I think before next stream, I'd like to make a sorted list of issues because we've been coming up with lots of them. I did. Okay, yeah, we'll have that for next time. Great. So, what now? I think I'd like to give myself a CLI interface that just spits out a binary. I'd like to try it on Pong, and then I'd like to run that Pong in the browser, and that can be our ultimate test of does our assembler work? And then, given that, we can start working on our own state machine. And you know what? I think as part of all that, I'd like to start breaking this down into smaller files. Yeah, we just need to organize things in general. So this is the assembly, the ASM package. This is just like the main package object. Um, I wonder if our assembler should just be an object with state, whatever errors and logging and whatnot. Let's start pulling out some types. So symbols, right? Symbols can go somewhere. Um, let's do a symbol.scala. Yes, I know. So steel trait symbol. Constants, the predefs, hard-coded symbol, user symbol, symbol object. Okay, there is a constant, which right now refers to an int. But are there any other symbols here? Okay, instructions use symbols. That's fine. this constant type. All of these layers have their own int opaque type class. I think we need to make that a system-wide thing. Um, what else? The symbols are just being used here. None are being defined here, yeah? Cool, this should compile. This should compile. Give it a sec. Okay, I think it's happy again. Yeah. Mm. And we're definitely not going to do this is upper, is lower thing. Yeah. Anything that's not predefined, we're just going to call it a user symbol. And like maybe there's a way to attach something from context, but that requires having a broader object that has some sort of context. So we'll take those out. What is this SP? Oh, right. I was thinking about this as a way to define our hard-coded symbols. We've got our virtual registers. We've got our hard-coded symbols. We've got to define whatever a constant is. And that will be across ML and the other. So we'll figure that out eventually. These comments aren't so helpful anymore. What is all of this? This is like our assembly model. I guess maybe this is like our program model. Yeah, our program is a list of these, which could be instruction. Let's put instruction in its own file. All right. Let's make inst. That's Scala. And where is inst defined here? Okay, so we have our seal trait inst. I guess this is a good tour of the repo as we're if you're coming in new to this. We have our a instruction, either a constant or a symbol. Um, registers. Do we need those here? I guess registers are part of something. They're part of our C instructions. They're needed there. Okay, bin up, extends comp. I think comp, I'd like comp to be its own file eventually. So we'll just put C instructions. Enum jump. Jump is used in the comp. It's using the C instruction. Okay, so we have a C instruction. We have parsers for C instruction. Okay, let's check that the compiler's happy. Okay, looks like it's happy again. Sleep on compile. Okay, let's do comp. Um, I guess comp is a trait. Comp's a sealed trait. All right, these are all comps. They're all binary operations, which are comps. Now, these registers, these jump, those are all actually part of C instruction, aren't they? Let's go back to that CInst file or that inst file. Yeah, Add.asm is a set of registers. Comp is a comp, which is in a different file, but jump we'll put here. So let's put reg and jump here. Actually, that jump is identical. I think that's identical in the ML layer. And the ML layer itself might name registers. So jump and registers might go in a different package. Assembly and ML are both like part of the hack model. So maybe we have like a hack model package that has things like the register, the jump, whatever constant slash binary, whatever our int is. Eventually some sort of DSL. Make that more specific. Okay, that's all to say. I don't think reg and jump should actually live here. Now, what is this? This is our 2ML, our deref, symbol table, address. Okay, same kind of thing. All right, I think I'm gonna put all of these inside of a hack package. Mhm. Yeah, it's gonna break a bunch of files. This is where I should ask for an AI refactor, actually. I'll ask Copilot to do that eventually. Okay, and now we're coming down to the program itself. So let's make a program file here that defines what a program is. So program is a bunch of lines. This is what a line is. I think we want a to do for a deref program. Those lines could be instructions or labels. Instructions has its own file, but comments and labels can go here. I know some people just put like all of these in individual files, but I want things actually accessible. I don't want to handle tons of tiny files. Alrighty. Define a simple table. Deref. We need just an assemble method. And we have 2ml. What's this comment? Should be able to call .2ml on a single inst. Yeah, I'd like to be able to call 2ml on a single instruction. Can we? We can only do it on dereference A instructions, right? I would actually like that though. Yeah, doing it on some A instructions requires a symbol table. We could just make that a context parameter, a symbol table. Maybe. Maybe. That can be its own feature. Note to self, make this a feature. Or not a feature, like one of my own feature requests. Next time I'm gonna show up with a list of list of features I want to implement here. And the constant still needs to be moved to like a hack package. All right, so all that's left in this main package object, there's this model stuff that needs to go for the whole hack platform. But other than that, it's just the symbol table, the deref, the 2ml. So all the assembling helper functions. So maybe I should have like an assembler file. Let's start with this. Let's start with the main. Hey there, welcome. Sparse chain. Okay. Main def assemble. I suppose we would want a file name as our parameter. I kind of like to pipe a file in to the program. So maybe I'll allow it both ways. Are you familiar with Nand2Tetris? So Nand2Tetris is basically you start with logic gates and you go all the way to building like a working computer and a compiler on top of that to the point where you could write a Tetris program on a computer you understand from the lowest level all the way up. And right now I've written an assembler and I want to test it on some assembly for Pong. So I have this Pong.asm. This is assembly code for this platform. And I'm going to compile this into a binary or assemble this into a binary. It's thousands of lines long. All my other assembler tests pass at this point. And then I'm going to run this in someone else's emulator. Um, but the goal is to write my own emulator. I'll make it web-based and be able to run our own games here. So let's give ourselves a file name. SM file. Okay. Source set from file, ASM file, great. This is our usual pipeline, hack file. You replace the file name. Okay, great. And what is this? This is the PW. Oh, this is our printer, right? Printer writer, print writer. Uh, I'm happy just doing that with a print line for now. Yeah, let's do that with the print line instead. So wait a second. I don't think we necessarily want. Hmm. Okay, fine. We'll do it that way. We'll print to a file rather than to standard output. Because in this case, that's pretty big. And it does save me trouble of writing the file name. This is reasonable. Okay. Are we still compiling? No, we've introduced some issues here. In the package file. What's going on here? Wait, package.asm. Oh, we don't have reg. That should be not found reg. That should be in our instruction. Set reg. Did we delete that and not placed anywhere? Um, yeah, I think we lost it. Oh, here. Wait, maybe that's part of our comp. I think it's in comp. Anyway, here is our reg and our jump. We do want to preserve that. Well, actually, these are both part of C instructions. Now, let's not put it in here because they are not parts of comp. Well, necessarily. Reg does show up in comp. Those are used here. Okay. In Hindi language, bola? I don't quite understand. Welcome, Tom. All right. Let's fix this file again. So this file here just contains these helper methods. Oh, what was that to do I'd written here? Um, maybe make a symbol table a context parameter. Don't need this or this or this. Currently just doing a little bit of cleanup here, but I'm happy to give a tour if it's not the most understandable. Wait, what happened to constant? We delete that. Um, type constant. Right. So we do want to keep. This is actually the kind of refactor I should delegate to AI. But it's kind of nice to see what's happening. Inst is defined. There shouldn't be a trait inst here. Oh yeah, all this inst stuff needs to go away. Now, how much context does I think part of what this is doing here in our 2ML is we are skipping over lines, over comments and labels. But if we had an actual like deref program, we wouldn't need that. And we can do like .ml on each particular line, as long as we have the symbol table when necessary. Okay. Are we back to compiling? Yeah. Well, now we can run. Now we can run our assembler. So let's run it on Pong. And what's the file name? Source main sources slash Pong.asm. You want to run assemble. Okay. Now let's look. Is there? Yo, how's it going? Welcome. There should not be a Pong.hack. Cool. Um, yeah, what do we do with this? Let's pull up the browser. So this should have an emulator for us. Hardware simulator, CPU emulator. I don't have a favorite. I will take whatever works. I don't have strong opinions on front end stuff. And when I do this in the front end, when I do my front end portion here, I'm just going to use Scala.js since I'm running the whole thing in Scala already. And in that case, I just defer to SBT. All right. So how does this assembler, or how does this work here? So there's a screen, there's a ROM, there's RAM, great. Load an ASM or hack file. Select local file. Okay, so what we're gonna do, actually, I'm gonna load this from, I'm gonna put this on another screen so I don't show what's in my file directory. But let's copy this to, okay, I'll load up that Pong.hack. All right, so this is the binary file I just assembled, and we're gonna run it. Okay, so stuff is happening. Should I be running this faster? I know what I'm seeing. Okay, we're only 500 steps in. 500 cycles, that seems like not enough for anything significant to have happened yet. I suppose I want to enable keyboard. All right, it sees what arrows I'm hitting. This keeps changing. There's some loop that's running. Hmm. Let's pause this. We'll clear the memory. Let's load up one of their assembly files. Does that work? Okay, so we've loaded up. This is what's in ROM, and it's showing us the assembly version. Oh, I actually kind of like that. As it's showing all of the, it looks like all the A instructions are dereferenced. That is helpful. But let's run this. So this is what happens when you run their built-in assembly. Maybe I pause. Let's change the execution speed, make it as fast as possible. Let it run. Oh, yeah, now we're hundreds of thousands of steps in. I don't know what I'm supposed to be. I don't know how to run this. Hmm. All right, I know there's also like an offline JVM version. In the first iteration of Nand2Tetris, the first edition, when I did it, that's what you did was you downloaded a Java program and ran it. It's gonna be old stuff though. Okay, the Nand2Tetris software suite. I just want to download. Yeah, I agree there. If you use, oh, you can use Codex or Claude to learn to code, but I'd be careful to actually like give yourself space to learn and not just let it do everything for you. In fact, I probably would just use ChatGPT. Use it to ask questions. Use it to ask questions about code. Or just use your Claude. Hook up your Claude or your Codex and use that to ask questions about the code base, about a line of code or something. I'd say like do that in your IDE. Like highlight a bit, ask a question about like what a piece of code does, and then like try writing some of your own code. All right. Let's see if I can get this stuff running. So what was that? That was yeah. Having the codex do work is fine if you review it. Um, but sometimes you like read things and you don't really understand it. Like the best test of your understanding is like actually writing it yourself. Right? Like you can read books all you want. That won't make you an author quite yet. You have to like try writing a short story at some point. So don't rob yourself of that chance. Okay. Unzip Nand2Tetris. Let's take a look at what's in there. Tools. And there is a CPU emulator. Let's look at that. Hope this still works with whatever version of Java I have running, and I don't have to like load up Java 5 or some weird thing. Because this is ancient. I think I did this like when I think it was like Java 6 when I did this. Okay, so let's run this. Wait, what's the parameter? We'll just have help. Wait, permission. Do I need to make it executable? What is the parameter that? Oh, okay, cool. An emulator just popped up on my screen. So this is the OG emulator from I don't know how many years ago, at least a decade ago. Have I done USACO before? Oh, that's like the coding Olympiad? No. I was closer to doing like when I was young, I was more into math. And I think I wanted to do the math Olympiad. So in my sophomore year, I scored like a 96 on the AMC, which if I scored like 100 or more, then that gets you an invite to the AIME. And from there, if you do well, you can go to the USA Math Olympiad. Um, and I never got another chance to take the AMC. And I wasn't big into coding back then. All right, so file, load program. All right. GitHub.com, stew squared, Nand2Tetris. Jeez, I wish you could just, I just want to pass a command line parameter. Okay, LMN. And I suppose source main resources. And we have Pong.hack. There it is. Okay. And now we can run this. It's running very slowly. How many instructions are we at? It doesn't give us, oh wait, the program counter here. It doesn't give us like the number of clock cycles that I've run. Let's stop this. Animate program flow. Program and data flow. No, let's do no animation because I think we just want to run this fast and let the screen go. Oh, okay. Well, it immediately did this. Okay, that's something. Let me make this bigger. Okay, so let's load a different program. Can it just work with an assembly? Hack or ASM file is cool. So we'll run the assembly and see if we get the same result. Okay, so this is working. Oh, and it's instantly game over pretty soon. Okay, cool. So the assembly works. I don't know why I couldn't get it to work in the browser, but apparently the hack file itself doesn't work. There's some bug in it. We're not going to debug that entire hack file. Um, so I suppose maybe we'll catch this as we're building the emulator layer. We need a we need a bigger test suite. We need debug features. Okay, let's try again with a hack. And let's run it slower and see if maybe we can get some insight before it crashes. So here, the hack file. Um, let's animate everything. Program and data flow. We'll run it a little bit slower. Oh boy. Never mind. I don't want that. Uh, that's not useful at this level. Let's animate the program flow. At what point does it hit a bug? And it looks like this just crashed. Okay, let's give up on this for a sec. Um, wait. Okay, when there's no animation, we could run the screen. Right, when we're animating the whole program flow, I think it's just too much program flow is happening to actually animate the screen. But we immediately run into, okay, at line 112, destination is M, but A equals 24577 is an illegal memory address. Okay, let's try to make sense of that error message. I'm gonna use a bathroom. I'll be right back. This might end up being a cliffhanger. We'll see. All right, we're back. So let's try to make sense of this At line 112, destination is M, but this is an illegal memory address. Here, when we're saying M equals D, and that doesn't happen right away, that happens eventually. So looking at the source probably won't really help us a lot. I don't know, we could try that anyway. So let's look at Pong.asm. 112. Oh, wait, we want Pong L.asm. We want it dereferenced. And we want it after these comments. 112 plus another 9 lines. Here, this M equals D. This is it. Yeah, I'm not gonna make sense of that just staring at it. Because we have to like decompile this into source code altogether in our head. Um, I mean, I suppose we could look, we can compare it with like Pong.hack. I suppose like if Pong L works, so Pong L works, there's an issue with our Pong.hack. So there's some instruction that's being tested here that, or that's being run here that isn't being tested by our other binaries. And we gotta figure out which one that is. I think we just have to have a better test suite. Because I don't think we're really gonna reverse engineer that particular bug. Uh, like, well, what are we testing? We're testing against reference files. We test that dereferencing is idempotent. We don't test all the instructions. So let's say, right, there might be some comp here that's not being tested properly. So we can write tests for all of these comps. See what comp comes from parsing a raw string. Yeah. Let's test a few of them in a worksheet just to kind of think about like what these tests would look like. Because I'll bet it's somewhere in here. I imagine you don't need to test at the instruction level. The instructions are probably fine. I feel like those have been tested well enough. But with the comp, there are plenty of instruction variations that probably have not been tested. So let's say d equals m plus 1. That's a thing we can do, right? What does that result in? Oh, okay, there's d equals m, for example. Has no case with d equals m. Oh wait, comp is on the other side. Yeah, okay, let's go one level higher then. I think I'll like that. So inst, do a cinst that parse. d equals m plus 1. All right. So there's a destination. This means increment m, and then there's no jump location. And if we can just test all of the possible things. There are a couple of assertions we could make here. Like, for example, I know in these binary options, the left should always be D. Right? Or rather, like, we're assuming the left is always D. Let's check that assertion. Um, when we create a binom, oh, hold up, where can we put that? Is left always D? It's not. Because we can do something like scenes dot parse. Like in the sub, for example, D equals M minus D. That's a reasonable thing to ask for. If we get the comp from that, 2 ml. Oh, we can't do 2 ml on a single thing yet. So we have to do like 2 ml list that. What's going on here? Required. Oh, whoop, you don't want the comp. Okay, and this is what it looks like at the machine layer level. And MISD is a completely reasonable way to phrase it. Let's see, when we're parsing add, left plus right. Yeah, okay, we don't need to. Left isn't always D. Yeah, maybe we want to normalize it. To do always A or M on the right-hand side. Okay, so I think we'll want, next time we come work on this, we'll want to add like a .2ml method so we can test individual instructions more easily. Um, and it also could be our binary layer, right? Like when we turn our ML representation into binary, but I feel like it'll be easier to test anyway. So ML package, here we go. To binary. Let's see. Yeah, this looks super straightforward. Comp.bits is the only place I might want to like check on that. Yeah, I'm less worried about that. Could be an issue with one of these. I suppose I could test those. Okay, so we can write some sort of quick test for this, and maybe that'll help us find the issue. But really, I think it's probably more at the assembly layer. I could write an alternative assembler. Oh, you know what I could do is I could test our binary output against the output. Let's see, against the output from the web IDE. So if we look at assembler here, okay, we load up Pong. We translate that into, yeah, Pong.asm. And then we download this binary code and we compare that. All right, so we run translate all. Oh, that's really gonna do it. It's gonna animate it. We don't need it animated, we just need it done. This is too many steps. Okay, pause. Set the execution speed fast. Okay, that's done. Long-1.hack. Oh, okay, we don't need to open it. We don't need to open it. Okay. So, long-1 hack. And we can just compare that. So let's diff that long1.hack against. And part of the reason I have slight hesitation because assembly doesn't need to translate into identical hack files, right? Like I think there's a good chance that we're trying to go for the same thing. Okay, I'll need to better way it. Oh wait a second. We want to compare it against Pong.hack. And already, right? At Okay, we'll need a smarter diff. But there's an approach. At least we have something that we can kind of test against. And that's where we'll leave off. I think we find someone to raid here. So we're at least able to um, compile it. We have it working. we have it working with all of these test files and all the sample outputs as well. So it works for these smaller programs. These programs apparently don't hit everything. We know that the referencing works, so our A instructions are fine because we're able to turn Pong to Pong.L.asm, where that's dereferenced. The issue is once we turn this Pong L into a hack file, and it's not necessarily true that we need to be generating the same uh, hack bytecode, hack binary, right? So that might be the wrong debug approach, but still, we need more testing at some point, more assertions. Perhaps tightening up our model will help us catch things, tightening up our type system, because part of the hairiness that we've introduced in my approach here is we are modeling the assembly, we're modeling the ML language itself. This is a lot easier if we're just taking assembly and translating it directly into binary, but I want to have an intermediate model. It's probably somewhere in that intermediate model where we have some extra hairiness. Um, yeah. So we'll see. I'll think about how I can test that, and we can pick up with that next time. Okay, so we want software and game development. I am not logged in. I should log in. Here, I'm going to do this in a different browser where I am logged in. All right, quick peek if there's something that's interesting. Otherwise, I might not raid again. Oh, oh, oh. Of mice and mechs. Man, there's a lot of bytecoding these days. Oh, what is mice and mechs? It's a roguelike of some sort. Oh, I'm too tired. Okay, I'm just gonna call it a night. But thanks for stopping by. And again, it'll be next Tuesday. The goal is to start at 8. Sometimes like tonight and last week, I don't get on until 9. But 8 p.m. on Tuesdays. I'll be better about that.